Welcome to our module number 3 for our syllabus, and this is torsion. So for this module, we'll be discussing about torsion. So in many engineering applications, members are required to carry torsional load. So what is torsion? Torsion is a rotation caused by a moment, okay, on a material. So, for this module, you will be able to learn the torsion of circular shafts because a circular cross-section is an efficient shape for resisting torsional loads. Circular shafts are commonly used to transmit power in rotating machinery. You will also learn another important application, torsion of thin-walled tubes. Okay? So, torsion is our introduction to problems in which stress is not uniform all throughout. It is varying depending from a certain support and to up to a point of unsupported length. Okay, or assumed to be uniform. Okay, in if it is supported at both ends. So over the cross section of the member, another problem in this category which you will consider is the bending of beams. Derivation of the equations used in the analysis of both torsion and bending follows this step. So number one, you need to make simplify assumptions about the deformation based on the experimental evidence. Number two, determine the strain that are geometrically compatible with the assumed deformations. And number three, you use Hooke's law to express the equations of compatibility in terms of stresses. And number four, derive the equations of equilibrium. These equations provide the relationships between stresses and the applied loads. There will always be a relationship. Okay? So, torsion in a circular shaft. Circular cross-section remain plain. Hindi sila nag-warp compared sa cuboid where it will wrap and therefore the nadidistort yung ating cross-sectional area compared sa ating circular section na hindi siya nag-wrap and perpendicular to the axis of the shaft. Cross-sections do not deform. There is no strain in the plane of the cross-section. Okay? Ang pinag-uusapan natin dito yung cross-section which is hindi man opposite, which is if you can remember, recall our first discussion where I showed you the cross-section of a certain material. So yun, hindi yun nade-deform. Okay? So the distances between cross-sections do not change. Okay? The actual normal strain is 0. But of course, if the strain is no longer 0, of course there will be a changes in the distance. But when we are talking of torque, there will be no changes in distances between cross section. Okay, so if this is your shaft, okay, so this is your shaft supported at one end. This is a fixed end, okay, and this is a free end. If I am to rotate this shaft at this direction, if you're going to observe on the supported end, this is the supported end, there is no deflection. Okay, compared to the free end that we have here a deflection of angle theta. Okay, and we have here the distance from x, the distance x from the point of origin, and the rotation is what we call the torque. Okay, so we will be curious on this part of the torque. Okay, because on this part, on the fixed end, walang nangyaring rotation. Okay, so yan. Interesado tayo sa deformation on this portion. But of course, it is a straight line kasi linear. It is linear for a if it is being caused by torque for this example. Okay. For compatibility, To analyze the deformation in the interior of the shaft, we considered the portion of the shaft shown in figure 3.2a. So this is the 3.2a. So from an original figure of this, na-deform siya to this. And that is what we call the torsional strain. Okay, that is the strain. Okay, so at a ds, thickness of ds, and we have here the rho. The rho is the distance from the center to the point of application of the torque. And the change in the angle is d theta from an original point of d up to d prime. Okay. First, we isolate the segment of the shaft of infinitesimal length, dx, and then peel off its outer layer, leaving us the cylindrical core of radius rho. Okay, so radius rho, kung saan nagkaroon ng rotation. As the shaft deforms, two cross-sections of the segment rotate about x-axis. Because the cross-section are separated by an infinitesimal distance, the difference in the rotation, denoted by the angle d theta, is also called infinitesimal. Okay? So we now imagine a straight line, that the straight line CD has been drawn on the cylindrical surface. As the cross-section undergo relative rotation, d theta, CD deforms into a helix CD prime. So from an original form of CD, it is now CD prime. By observing the distortion of the shaded element, we recognize that the helix is angle G is the shear strain of the element. So the angle here is the element of the strain. Okay? Then from there, we can generate our equation. Strain is equivalent to d theta times rho divided by dx, or with respect to dx. The quantity d theta over dx is the angle of twist per unit length, where y is expressed in radian. The corresponding shear stress illustrated in figure 3.2b is determined from de Hooke's law. Okay, so this is determined from de Hooke's law. So you have here the shear stress. If you have a shear stress that it is towards that is clockwise, of course, to maintain equilibrium, there is a counterclockwise. And to the cross-sectional area, or our infinitesimal length, of course, there is also a shear acting. Okay. Then from there, with the help of Hooke's law, shear stress is equivalent to the G is modulus of elasticity for shear times the strain, or that is also equal to the modulus of elasticity for strain times the change in the angle with respect to x times the rho, and that is the strain. Okay. Note that G, d theta over dx, is independent of the radial distance rho. Therefore, the shear stress varies nearly with the radial distance free, rho. So the shear stress is varying depending on the distance from the centroid. Okay? If it is near the centroid, the stress is lesser. But as we go out from the centroid, it is increasing linearly. Lumalaki siya linearly. Therefore, we can conclude that the maximum shear stress can be found at the outer radius. Okay? So, dito natin makikita yung maximum shear stress natin. Okay? Yan. Equilibrium. So, for the shaft to be in equilibrium, the resultant of the shear stress acting on a cross-section must be equal to the internal torque. I repeat, The resultant of the shear stress acting on a cross-section must be equal to the internal torque acting on that cross-section. So figure 3.4 shows the cross-section of the shaft containing differential element of area dA located in radial distance r from the axis of the shaft. Okay, so this is the derivation of our equation. The rotation on the cross-section at the free end of the shaft, called the angle of twist, is obtained by integration. Okay? Theta is equivalent to the derivative of the angle of rotation from 0 to L. And theta is equivalent to T dx over Gj. Okay? Therefore, theta is equivalent to the torque times the length divided by the modulus of elasticity for shear times the polar moment of inertia. Okay? So kindly memorize this equation. So, torsion formulas. The shear stress acting at a distance r to the center of the shaft. For example, dito tayo, from the center or the centroid, papunta at a certain distance from the centroid, this is the formula. Okay? So, if we are interested to determine the maximum shearing stress, which is on the outer part, from the from the centroid, then we will use T times the radius divided by the polar moment of inertia. Okay? So, positive T or theta if it is rotating in a counterclockwise. Then negative if it is rotating clockwise, depending on the orientation. Okay? As long as we arrive at the same answer, then there's no problem. So, by Hooke's law, because of Hooke's law was used in the derivation of the equation, these formulas are valid only if the shear stresses do not exceed proportional limit of shear of the material in shear. Furthermore, the formulas are applicable only to circular shafts, either solid or hollow. So, polar moment of inertia, if you have here a solid shaft, ibig sabihin walang hollow sa loob, then we're going to use pi times the radius raised to the 4th power over 32. Or it is equivalent to pi d raised to the 4th power over 32. But if it is a hollow shaft, we're going to subtract the radius of the hollow raised to the 4th power from the radius of the outer radius of the outer shaft raised to the 4th power. So, tatanggalin natin yung hollow. Okay? But what is polar moment of inertia? Polar moment of inertia, or it is also known as the second polar moment of area. If time has permitted you from last sem, from your statics, you are lucky if you were able to finish the polar moment of inertia statics. Okay, but if not, then this is the formula. So, polar moment of inertia is used to describe the resistance to torsional deformation. Okay? Ito yung nagde-describe ng resistance ng material sa torsional deformation. Sa deformation due to torsion. Okay? So, the expressions of the polar moment of circular areas are given in figure 3.6. We obtain the following. So, shear max is equivalent to 2 times torque divided by pi r cube. Or just simply use our general equation here and here. Then, just simply input it. Just simply substitute J. Then there's no need for you to memorize this. But if you want to memorize this right away, then well and good. So shear max is 2 times the torsion divided by pi r cubed, or it is also equivalent to 16 times the torsion divided by pi d cubed. For the shear max, it is 2 times the torsion times the radius of the outer divided by pi times r of the outer raised to the fourth power minus r of the inner radius raised to the fourth power, or that is also equivalent to 16 times the torsion times the diameter of the outer divided by pi times quantity d raised to the fourth outer minus d of the inner raised to the fourth power. Okay, so for power transmission, in many practical applications, shafts are used to transmit power. The power P transmitted by a torque T rotating at an angular speed is given by P is equivalent to torque times the angular velocity. If you're, I believe you're already quite familiar with this angular velocity from your hydraulics no, you are taking up your hydraulics right now. Anyways, you will be meeting this more often. You will be meeting angular velocity in your hydraulics right now. Okay, so this is the formula for power transmission. Okay, so torque is equivalent to P divided by 2 times pi O times F. So 2 pi F is your angular velocity. Okay, so for problem solving, it would be a handwritten.